Little g?
Yeah, little g.
Acceleration due to gravity.
Thank you.
There you go.
I heard acceleration at first, then I heard gravity, and I don't know if you said acceleration or gravitational acceleration or something like that.
It's MG.
That, I thought you said it, though. Repeat it. All right, so I've got ft cosine theta equals mass times, all right, I got this acceleration here. What, it is centripetal acceleration. What's the formula?
Oh.
Oh. V squared over R.
And then the second equation, got ft sine theta. I'm gonna go ahead and bring the w over equals mg. All right, now it's a matter of solving. I want to find period. I really need to find speed first before I can find period. And now it gets into, there's the easy way and the hard way. Part of me wants to do the hard way, so you appreciate the easy way. And part of me thinks, I want to do that to them.
I imagine that part is gonna make quite.
We can save some time by doing the easy way first.
Or I will just leave it up to you.
Easy.
What do we do next? Not whether easy or
Oh.
hard, but how do you actually solve? We want to solve for V. I don't know tension. I don't know theta. I don't know V.
I know the hard way would be like to, since that the cosine and sine are oscillating functions, and then we just find which area what type, what period it is at that degree, and then we just go from there. Does it make sense?
That did not.
Oh, so like,
Laura?
Do we divide the top equation from the, we do that?
What would that do?
It would help us to, well, FT divided by FT.
Okay, so it get rid of our tensions.
Yeah.
All right.
Get rid of our tensions and possibly our M's.
It will.
Okay.
So what I'm gonna do, ft sine theta is equal to mg, and ft cosine theta equals, that's mv squared over r. Oh, I don't know r either. Got a bunch of unknowns here. If I divide top and bottom here, tensions cancel out, I'm left with tangent of theta is equal to, my masses cancel out, I'm left with rg over v squared. Now, there is a relationship between theta and r. And v, because the faster it spins, the smaller theta is going to be. Let's just start out with the relationship between r and theta.
You multiply it by 10. So you could, it would go on the other side, is that what you're trying to do?
No, I
You're
need
trying
to separate, based upon the geometry over there, the relationship between r and theta. Okay, first off, what is r?
the radius.
The distance from which, all right, so r is the distance from here to
The center.
this, here,
No?
or here,
Yeah, the top part.
go up there?
Yeah.
Yeah.
When did r pop in over there?
When we
That's-
put in the centripetal acceleration.
Right, and in the centripetal acceleration formula, what's r? Will you say it, Abigail, and I missed it?
No, I'm trying to say that it would be the horizontal way, because R came in the equation over on tension cos theta, so wouldn't that be?
Yeah, it came in because of this,
Right.
right there. R is the radius of the circle. And the circle, it's a horizontal circle, so r is that.
Right.
Let me give you this length right there, that's L. What's the relationship between r and theta? Or relationship, I got L, R, and theta.
The arc length is equal to
No, the arc length equal to r theta, that's a different theta. This is a right triangle trig.
Is it the opposite? The R would be opposite from theta, which theta are we looking
This theta right here.
at? Okay, so G.
I have a right triangle here.
Yes.
I have an angle theta, I have an adjacent side, I have a hypotenuse.
Yes. Oh,
They're the
that
cosine
is,
of each
that
other.
is tangent.
So the adjacent is R,
Adjacent is r.
right?
We can,
Never mind.
Yeah. I know that r is equal to L cosine theta. So I can plug that in, get rid of an unknown there, so I have, so this is equal to L cosine theta G over V squared. I can solve. Ultimately, I'm trying to find period there.
In, question.
Yeah.
In between theta and G, is that anything over there?
In between theta and, oh, here,
Yeah.
it's a parenthesis.
Um,
I put the parenthesis there because I didn't want it to look like we were doing the cosine of theta G. It's cosine of theta times G. Period. Time takes to go around. What do you know about that? Or try it again. How do we define the speed of an object if the speed is constant?
the initial plus final divided by 2, is that what you're asking for?
Something simpler than that. If speed is constant,
Is it distance over time?
yeah.
Distance over time?
So speed is distance over time. If I'm looking at something traveling in a circle repetitively, the time to go around once is the period. What about the distance this travels in?
Circumference.
And the formula is, somebody said it.
2 pi r.
And I know that r is equal to L cosine theta. So T is 2 pi L cosine theta divided by, I'm gonna leave it there. So V is equal to 2 pi L cosine theta divided by the period. So if I plug that in, I now have L G cosine theta divided by 2 pi L cosine theta over T squared. That one's nice.
We can cancel.
So I have tangent of theta equals, so I got L here and L squared down the bottom, so I get L on the bottom. I have 4 pi squared. I got a cosine squared and a cosine, so I get a cosine theta. And see, G is still on top, and I get a T squared. Take a moment just to make sure I didn't make a careless error, because I did 2 steps at once. So 4 pi squared on the bottom, I'm good with that. T squared on top, I'm good with that. L cosine theta, cosine theta, yeah.
So could you cancel out the cosine theta denominator by canceling it from tangent to get just sine?
Say it again?
So since that tangent is equal to sine divided by cosine, can you just like cancel out the cosine from the denominator by moving it to the other side?
Okay, so that's sine over cosine, so I get sine of theta is equal to GT squared over L 4 pi squared. I still have 2 unknowns. change the formula there, other than it would just change the number we plug in for G. Assume you know L, assume you know M, although M has disappeared.
So that's L for pi
Square.
squared cosine of
Yes.
Okay.
Keep wondering if I'm missing something here. I don't think that we've made any mistakes. That I feel like. Let's see.
Or squared. Still squared.
I figure out data theoretically is.
So was this the hard way?
Yeah.
Okay.
All right. Let me just do the easy way in my head for a second. Losing way. Oh, I know what I'm doing. Wrong. Okay. Yeah, I do need to give you another piece of information. The problem we started out doing, we had another piece of information which we don't have here. So, all right, so let's. I should have stuck to, we're just sort of exploring. Got this. So let's change the problem.
I wrote this in pen.
I'm gonna have it 200 gram wake here, and hopefully the string won't break. Now, if I just let go, this will fall. I hope you recognize that. At the other end, I have a potentially dangerous situation here.
I
Really quick question. So
Yeah.
how far back are we going from what we were just talking about?
Just.
He's gonna give us another piece of the puzzle, or.
Yeah, we're gonna make this a realistic problem. Force diagram doesn't change. I don't think we're going back too far. All right. So the question is, hello. That attached. I want this attached. How fast do I need to swing this so that the 200 gram mass doesn't move?
Oh.
honestly, I
All right, right now it's rising. Let's get it over there. All right, so let's assume that that's about a thumb's width, that knot right there. So the question is, how fast does that need to spin in order for this 200 gram mass to be in equilibrium or close enough?
Very fast.
All right, so what we're gonna do is,
Oh. Honestly, bring it. I'll need to have this glass anytime soon.
You survived today.
seems like there was a rubber stopper. So I'm not swinging a piece of metal. Ah,
Oh,
there it is.
okay. A bit better.
Yeah, this is a more solid string.
Wait, so when you're rotating the top piece, the bottom piece is going up?
if I swing it fast enough.
Yeah. Now say the question again, I was preoccupied with something else while you're doing that.
Oh, let's put the 200 here. All right, so how fast do I need to swing this so that the 200 gram mass does not move up and down?
Very nice.
All right, so if we could time how long it takes to go around, people with stopwatches on their phones, or let's get this set up.
Start.
All right, I'm gonna say go. We're gonna time 10 revolutions. All right, ready? 2, 1, start. 2, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's hope that those two numbers are really close to each other. What'd you get?
5.56.
0.56,
5.56.
5.56.
5.30.
Pretty darn good. Can we get another one?
I also got 5.30.
I got 8.
8.
Let's just toss that one out for right now. I don't know what it was, but, all right, so I got those three numbers right there. What is the average time?
Yes.
And that was for 10 revolutions. So my period,
To divide by 10.
the period is 0.539 seconds. Remember, period is for 1 revolution, and these times were for 10. Just wait till you do the lab and you're swinging that thing 20 times per trial.
When is that?
Your arm gets- That would make sense. All right, so we have the time. Now the question is, what are lengths? I can measure L. I can't measure R because that would require knowing the angle at which this mass was down. There was a black mark on the string here, so that sort of keeps, so I know where the string was in relationship. There's the black mark. And the black mark at the bottom of the tube there. And so I just need to measure the length from the top of the tube to, in essence, the center of mass there. So L is, looks like 62.5 centimeters.
And then we're trying to find theta. Essentially.
God, there's so many things that we could do. Sure, let's find theta. And
R.
no, let's find the mass that we're swinging. So we don't know M. So that's 0.625 meters. And the hanging mass, I'm gonna trust them for some reason. It's 200 grams. So I had something hanging down here. This was 200 grams. This is a crude enough thing. I'm just gonna make the acceleration. No, let's use 9.8. I won't use the 9.796 or 798. So that's 0.2 kilograms, assuming that they didn't lie to us. So the weight hanging down, the tension in the string would be 0.2 times 9.8, or 1.96 newtons. What? All right, so we have a marker here. So this is the setup. I've got a tube right here. I have a mass hanging down. I have a mass swinging. So this is swinging in a horizontal circle, in theory. This was a 200-gram mass. Now, for the sake of a class demonstration, I'm gonna trust them. In actual lab, I wouldn't trust them. So that's 0.2 kilograms. And so the weight hanging down here is 0.2 times 9.8, which is 1.96 newtons.
Oh, okay, sorry, that's where I was confused where you got that from.
If this is an equilibrium, then the weight should be equal to the tension in the string here. If we assume an ideal situation, which we're going to, the tension in the string here should be the same, should be 1.96 newtons. That's why I wrote over there, the tension is 1.96 newtons.
So with whatever weight we find for that full ball, we can multiply it by 9.8 and we should get the same for 1.96? No, because we're not, never mind.
Yeah, no, it doesn't,
Confused
because
myself.
if you recall, we had ft cosine theta is equal to mv squared over r, and ft sine theta is equal to little mg. So we're trying to find this mass here.
Right.
So you're saying that the weight of the mass is 1.96 newtons, but the tension on the one that we're trying to find, the mass that we're trying to find, is the 1.
It's also 1.96.
Okay.
That we're assuming, I'm making the assumption that our string is close enough to ideal, that the tension at each end is the same.
Okay.
I figured that the weight of the string is negligible, and that I'm also figuring that any friction along the edge of the tube is also negligible. Now, that's probably, of the two assumptions, that's probably the bigger leap I'm taking.
So does
But
that,
it's relatively smooth here, so I don't think it's that far off.
does that imply that M cancels out FT, since that they're equal to each other?
It implies what?
Does that imply that M cancels out with FT, so we only have sine equals G?
Well, no, because the end that we're looking for now is not the mass of the 200-gram object, it's the mass of the.
Swinging.
Okay,